So here goes your crash course in organic chemistry, and hopefully you won't feel like you're dying throughout it. We'll explain that joke later, but hopefully you'll get on okay with it. But just to introduce you to organic chemistry is essentially the study of anything to do with carbon-containing compounds. So compounds that contain carbon, that's what organic chemistry is all about, looking at their properties, their structure, their reactions, and so on. So anything that contains carbon, that is what organic chemistry is all about. And they exist in families such as alkanes and alkenes, and that depends on the structure of the carbon compound, the bonding within it, but we'll have a look at that later. The first thing we want to look at is the source of hydrocarbons. Where do we actually get hydrocarbons from? And the main source is crude oil. And that's sometimes referred to as petroleum, but you're better using the term crude oil. Crude oil is essentially unprocessed oil which we find underground. And crude oil is classified as a fossil fuel because crude oil is made from dead and decaying plants. So plants and animals that died and were covered by a layer of mud, and due to pressure and heat, crude oil was formed. And we can use it as a fuel when we separate it, which we'll look at later. But you need to be familiar with these terms, fossil fuels and renewable and non-renewable energy. Terms that you've met a long time ago, but your specification requires you to be familiar with the definition of these terms. So fossil fuels, they're fuels formed from dead and decaying plants and animals over millions of years through the action of heat and pressure. Treat these as definitions that you need to learn. Fossil fuels, we know that they're non-renewable. They're made over millions of years, so we can't exactly make them very quickly. We can't regenerate them very quickly. They take millions of years to form. So once we use them up, that's them used up. We can't regenerate them. And they can't be replaced within a human lifetime. If you think of a human lifetime, well, now the average life expectancy is 100 years, but even still, in 100 years, you could not make fossil fuels. So that's why we call it non-renewable. So they're going to eventually run out. Whereas we've got other energy resources, such as solar, wind, tidal wave, geothermal. They're renewable because we can regenerate them. They can be renewed within a human lifetime, and so they won't run out. And it's important that we explore the use of renewable energy resources because traditionally we've used fossil fuels, but we know that they're going to run out, so we need to explore the use of renewable energy resources. So be familiar with those terms: fossil fuels, non-renewable, and renewable energy. So what actually is crude oil, and how can we actually use it? Crude oil it's a black viscous liquid. That just means viscous means that it's thick liquid, a bit kind of like caramel. It doesn't burn easily, so crude oil in itself, just taken straight from the ground, is not much use to it, and that's because it's a mixture of these hydrocarbons. Think back to your definition of hydrocarbon at the top of the page. A compound that consists of carbon and hydrogen only. So crude oil is a mixture of these hydrocarbons, which contain from 1 carbon atom up to 70 carbon atoms. So a hydrocarbon with just 1 carbon atom would look like this. So 1 carbon with 4 hydrogens attached to it. So you can have just a very, very short hydrocarbon with 1 carbon, in it, or you can have up to 70 carbon atoms in crude oil. And that would be a chain of 70 carbon atoms. There's 7, think of 10 times as long as that. And then they would be surrounded by hydrogen atoms as well. So you can see you've got a real mixture here of hydrocarbons from very short to very long. And that's what makes crude oil itself very useless. Because it's not much use to have these mixture of hydrocarbons. So we need to separate them into simpler hydrocarbon mixtures. So rather than having one large mixture of carbon chains, anything from 1 carbon to 70 carbons long, we'd put them into smaller groups. So for example, group the chains that have 1 to 4 carbons together. So I'd put all these ones together. And then maybe group the ones that have 5 to 12 carbons in their chain together. And then we could group the ones that have 12 to 16 carbons in their chain together. Put them in a separate group. And then ones with over 16, just for example. So we're taking one large mixture and we're separating it into smaller mixtures that contain carbon chains of a similar length. And we do this by a process called fractional distillation. And from last year you should be familiar with simple distillation, and we perhaps focused on this in terms of separating a solution. So for example, salt dissolved in water, we can use distillation to get our salt but also retrieve our water as well. But we did talk about how we can use simple distillation to separate liquids that have different boiling points. That's the principle by which distillation works, that we're separating liquids because they both have different boiling points. So take here the example of water and ethanol. The water and ethanol fully mix, they are miscible liquids, and both colourless liquids, so it would be difficult to separate them. So we use distillation, and how it works is that ethanol has a much lower boiling point of about 78 degrees than water. Its boiling point is 100 degrees C. So I heat my mixture of water and ethanol, and what happens is when it gets to 78 degrees C, the ethanol will start to evaporate. So in my mixture we'll get the ethanol evaporating, and the temperature on the thermometer will be 78 degrees C. It will then pass into your Liebig condenser. And once it passes into the condenser, remember we have cold water going in at the bottom and out at the top. And that cold water is running around the outside tubing, and it is keeping the condenser very cold. So when my ethanol vapour, ethanol gas, passes into the condenser, it is cooled by the condenser and it condenses back into a liquid, and we get liquid ethanol being collected in our beaker. And the ethanol will all separate out when my mixture is at 78 degrees. And when all the ethanol has separated out, the temperature of our mixture in the round bottom flask here, it will start to rise again. So I can remove this beaker here and remove my ethanol from it. And then the water will start to evaporate. Water will evaporate and pass into the condenser, and it will condense, and I can collect it in a separate container. So that's how I can use simple distillation to separate a liquids that have different boiling points. Fractional distillation works by the same principle. It's just a little bit more complicated in that your mixture contains many more different liquids, but the same principle. You put your mixture of liquids into the round bottom flask, it's heated, and you can see this fractionating column that separates out the mixture into the different liquids, or what we call fractions. which are those smaller groups of different liquids, so smaller mixtures. So that's how fractional distillation works. It's for mixtures that contain many more different liquids, and it's separating it out into the different liquids or into these fractions, so smaller groups of liquids. And just like with simple distillation, it works by that process of evaporation followed by condensing. So your liquids with the lower boiling points will evaporate first, pass into your condenser to be turned back into liquids and be collected. And then your liquids with slightly higher boiling points will then start to evaporate and then pass into the condenser and be condensed and collect in a separate container. And then liquids with a higher boiling point again will evaporate and then condense back into a liquid in your condenser. So distillation, whether it's simple distillation or fractional distillation, works by a process of evaporation followed by condensation. Evaporation of your lower boiling point components followed by the condensation of them, and then after they've separated off, evaporation of the components with a higher boiling point. And it's this process of fractional distillation by which our crude oil is separated, and it uses fractional distillation to separate our large mixture of hydrocarbons into smaller groups of mixtures based on their boiling points, and they're collected in simpler mixtures called fractions, as we discussed earlier. Now at this point it would be worth watching the video that I have posted in the comments section of this video. It's a helpful video on how fractional distillation of crude oil happens. So watch that video before moving on in your notes. So hopefully you will have some idea from that video of how the fractional distillation of crude oil works. And you've got a diagram on page 5 of your notes that hopefully helps you with that as well. So you'll see here that we have our fractionating column in the middle. But we start with our crude oil, and it is a liquid. And in order for fractional distillation to work, we need our liquid crude oil to evaporate first. And that's the purpose of the furnace. So once we heat our crude oil up, it'll turn to a gas. And crude oil is a gas as it enters into the fractionating column. So it is perhaps at about 350 degrees that it enters the fractionating column, and it is not heated once it enters the fractionating column. So what happens is the gases will rise up to the top, and as it rises up to the top they will cool down as it is not heated any further. So it actually gets colder as you rise to the top, so the temperature decreases as you rise up the fractionating column. So it's 350 degrees when it enters the fractionating column, and then as we rise we might get to about 300 degrees, and then it might cool down to 250 degrees about here, 200 degrees as we rise to here, 150 degrees C, and by the time we're up at the top it's much cooler at about 100 degrees C. And as the gases rise up through the fractionating column, once they reach their boiling point, they will start to condense as liquids and be separated off. How that works, if you think about what is happening, if you've got a liquid and it reaches its boiling point, it will turn into a gas at its boiling point. But say you've got it as a gas and you cool it down. Once it reaches the boiling point is also the point at which it turns back into a liquid. Think about water, for example. Say we had water at room temperature at 20 degrees C and we heated it up to 100 degrees C. It would turn into a gas, it would turn into steam. But say we had some steam at 200 degrees C and we wanted to turn it back into a liquid. Well, we would have to cool it down, and once it got to 100 degrees C, it would turn back into a liquid. So it's the same principle by which this fractionating column is working. When the gases reach their boiling point, they will start to cool down and turn back into a liquid. They will condense into a liquid, and that's the point at which they leave the fractionating column. So let's take 6 different hydrocarbons and see what happens to them as they are separated out in the fractionating column. So you can see here my little key at the side, and we've got red, orange, yellow, green, blue and purple. And the red is the hydrocarbon with the longest carbon chain, and as we move from red down to purple, the chain gets shorter. So the carbon chain gets shorter, and you hopefully learned from the video that the longest carbon chain is the one with the highest boiling point, and the one with the shortest chain is the one that's going to have the lowest boiling point. So you can think of the boiling point as being proportional to the length of the carbon chain in your hydrocarbon. The longer the hydrocarbon chain, the higher the boiling point. The shorter the carbon chain, the lower number of carbon atoms in a hydrocarbon chain, the lower the boiling point is going to be. So let's pretend these hydrocarbons come in one by one and see what happens to them. So first of all, we've got our red hydrocarbon, and that's the longest hydrocarbon chain. So let's say it has a boiling point of about 320 degrees C, for example. Okay, so it comes into the fractionating column, and once it gets to 320 degrees C, it is currently a gas at 350 degrees C, but once it gets to 320 degrees, any lower than that, it's going to turn into a liquid. So once we reach about 320 degrees C, it's now turned into a liquid, and once it's a liquid, it can be removed from the fractionating column. Okay, so once it has reached its boiling point, once it has dropped down to its boiling point, it'll turn back to a liquid. Let's take the orange hydrocarbon now, which is slightly shorter. What that means is that it'll have a lower boiling point, which means it'll stay a gas for longer. So it comes in the fractionating column, and it will rise up the fractionating column until it gets to its boiling point of, let's say, about 270 degrees C. At that point, once it's cooled down to that point, it can no longer be a gas. It condenses as a liquid and is separated off. The yellow hydrocarbon is shorter again, and let's say it has a boiling point of about 230 degrees C. At 350 degrees, when it enters the fractionating column, it's going to be a gas. And again, it's going to rise up, rise up, rise up. Once it cools down to 230 degrees, it's no longer a gas. It condenses as a liquid and is separated off. The green hydrocarbon now, let's say it has a boiling point of 175 degrees C. At 350 degrees, therefore it's going to be a gas because it's above its boiling point. It rises up the column, and once it gets to 175 degrees, once it's cooled down that far, it will condense as a liquid and separate off. Again with our blue hydrocarbon, shorter again, so it's going to have a lower boiling point. Therefore it's going to reach even further in the fractionating column. Still a gas, still a gas, still a gas. But once it reaches its boiling point, it cools, it condenses, and is removed as a liquid. And finally, the purple hydrocarbon, which is the lowest or the shortest carbon chain, so therefore the lowest boiling point. Let's say it has a boiling point of about 60 degrees C. It will be a gas until that temperature. So it enters into the fractionating column. It's 350 degrees, so it's still a gas. 250 degrees C, it's still a gas. 150 degrees, it's still a gas. Until it cools right down to 60 degrees C, and in fact, it can be removed as a gas, because at the top of the fractionating column it's still 100 degrees C, so our shortest carbon chains are going to be removed as gases. So it's kind of opposite to what you think. The top of the column is the coolest part, and therefore the ones with the lowest boiling points are going to rise up to the top, and the ones with the higher boiling points are going to be separated off at the bottom. So probably the most important thing to label your fractionating column with is that down here you have the highest boiling point, so they are going to be the largest or the longest hydrocarbon. And at the top you have the group of hydrocarbons that have the lowest boiling point, and they are the shortest hydrocarbon. And it's important that you remember that at the bottom you've got your highest boiling point with the longest hydrocarbon chains, and at the top, you have the hydrocarbons with the lowest boiling point, and they are the hydrocarbons that have the shortest chains. So you have to remember the purpose of fractional distillation of crude oil is to separate them into the mixture of hydrocarbons into simpler fractions or simpler mixtures of hydrocarbons that can actually be of some use, because crude oil, there's far too many different components in that mixture for it to be useful. So we separated it into simpler mixtures that can actually be of some use to us. And what the fractions are named according to what their use might be. And you do need to be familiar with the different names of the fractions and what they are used for. So this table on page 6 is really important. You need to know the fractions and some associated uses. And you'll notice that they are in order of how they come out in the fractionating column. So bitumen is the fraction that comes out at the bottom. And think about what that means. The fractions at the bottom have the highest boiling point, and they are the longest hydrocarbon chains, the group of hydrocarbons that have the longest chains. So you might have 20 carbons in the hydrocarbon chain of these particular hydrocarbons. So bitumen is used for waterproof roofs and pipes and tar for roads. And as we rise up here, our chains are getting shorter, our boiling point is getting lower, until we reach the top of the fractionating column where our refinery gases come off. And that's going to be the top of the fractionating column. They're the hydrocarbons with the lowest boiling points, so they condense off last, and they are our shortest hydrocarbon chains, and they may only have anything from 1 carbon long, and I'll just draw in the hydrogens at this point as well. So they may only have 1 carbon long surrounded by 4 hydrogens, or my chain might be 3 carbons long and surrounded by hydrogens, and we'll talk soon about how many hydrogens we put around our carbons. But you'll see these refinery gases are used as bottled gases, so when they are removed from the fractionating column, they are actually still gases because their boiling points are so low. And so they are transported as gases. They're gases at room temperature. And they're used for gases such as methane or butane that are used as fuels. And we use methane as our gas for the Bunsen burners in school. So gases like methane or butane that are used to burn for fuel. So you'll see there's 6 different fractions that you need to know about. You need to know the name and the associated use of those different fractions. And you'll see lots of everyday uses for the different fractions of crude oil, which makes crude oil so important to our everyday life. And it's why we have to be conservative of it, as it is a fossil fuel, but it's something that we use every day. So for example, the petrol fraction is used for petrol for our cars. Naphtha has pharmaceutical uses in the manufacture of drugs, but also for plastics like our bottles and all other uses of plastics, and even for things like detergents for washing up, and kerosene used for aviation fuel, so fuel for airplanes, and diesel oil used for cars, but also for agricultural and industrial machinery and things like lorries and large vehicles. So lots of everyday uses for the different fractions of crude oil. But as we said, fractional distillation is the important process by which crude oil is separated out into the different mixtures that actually can be of some use to us. Moving on down page 6, then you will see the area of this topic that looks at the pollution from fossil fuels, a lot of which we have covered before in previous topics, but this first one will be slightly new to you, and that is the problem of the pollution caused by spilt oil. So crude oil is transported around the world to be separated by fractional distillation, by ship and by road, by boats and by lorries. And then once it's in its fractions, it will be transported again to places that need to use it. But particularly when it's being transported at sea, it can have major environmental problems. And that's because if it is spilt, you will know that oil and water do not mix. So if you have the sea and crude oil is spilt, it will form a layer on the top of the sea. So if you have an animal that needs to break the surface of the water, it will get covered in oil. And the most common example is diving birds who dive to get fish to eat. If they dive through the water, I'm not going to attempt to draw a bird. If they dive through the water, they're going to get covered in oil. And once they're covered in oil, and their wings are covered in oil, then they're not able to fly. And here you can see a picture of a bird that has been covered by oil. And other aquatic life can be affected as well, particularly mammals such as seals, dolphins and whales that live in the water. If they get covered in oil, that can be very harmful. So over on page 7 you have a list of the problems associated with oil spillages. And the first one is what we've just been discussing about, that it harms diving birds, as we discussed in the previous page. It's also not very pleasant to look at, and we call that being an eyesore. So it creates eyesores on beaches and shorelines. And we would have talked about the idea of eyesores when we were talking about limestone quarries, how they create eyesores, so things that are not pleasant to look at, and they also destroy habitats. And those are your 3 major problems associated with oil spillages. Other forms of pollution of hydrocarbons and fossil fuels include the greenhouse effect, again which we will have talked about before now in the last topic, when we talked about the combustion of carbon. When carbon is completely combusted, it forms carbon dioxide, which is a greenhouse gas. And at the time we would have talked about how when carbon dioxide is produced, it forms this layer around the Earth in the atmosphere. Forms this layer, And when the sunlight energy moves towards Earth to heat the Earth, our Earth's temperature is regulated by the fact that some of the sunlight is reflected away from the Earth. But if we have this layer of carbon dioxide, it will trap some of the sunlight and reflect it back to the Earth, and that will trap some of the heat in the Earth's atmosphere, which causes the Earth's temperature to rise. And as we talked about at the time, that causes global warming. So global warming is literally the warming of our globe, of the Earth. So the temperatures of the Earth rise, and that leads to polar ice caps melting. Which leads to sea levels rising. So if the ice caps at the North Pole and the South Pole, they melt, that's going to add more water into the sea, which causes the sea levels to rise, which does lead to localised flooding. If you can fit that in there. Particularly of seaside towns. And just in general, it causes climate changes if the Earth's temperature is warmer because of the greenhouse effect. So a situation that we've talked about before, but you do need to know the effects of the greenhouse effect, particularly when you're talking about the burning of hydrocarbons, because remember that hydrocarbons, they're compounds containing hydrogen and carbon only. So they contain carbon, and when we combust carbon, we get carbon dioxide, and that leads to the greenhouse effect. So how do we minimise the greenhouse effect? Well, we use alternative renewable sources of energy, for example, wind, wave, solar energy, or we use clean fuels such as hydrogen. We talked about that in Unit 2.7, our last topic of non-metals. And that's because when we burn hydrogen, we're really reacting hydrogen with oxygen. When you react hydrogen with oxygen, you get water. And if you want to balance that equation, you'll need a 2 in front of your water and a 2 in front of your hydrogen. So that's why hydrogen is considered a clean fuel, because its only product is water, and water is not harmful. It's not a polluting gas. Or we can use fuels which are slightly cleaner than our fossil fuels, such as ethanol, and we'll see that later on in this topic. Another form of pollution from burning fossil fuels is that of acid rain, and this happens when our fossil fuels contain traces of nitrogen and or of sulfur, and that is because when we burn nitrogen, we get a mixture of nitrogen gases, and that we call them NOx gases because it could be nitrogen monoxide, could be nitrogen dioxide, could be nitrogen trioxide. So a range of nitrogen oxides. And sulfur, when it burns, we get sulfur dioxide. And these are polluting gases because what they can do is they can dissolve in water, dissolve in rainwater, and then they will fall as acid rain. They're acidic gases, so when they dissolve in water, they make the water more acidic. They lower the pH of the water, and it will fall as acid rain. And we learned in our previous topic that the effects of acid rain are things like corrosion of limestone buildings, or limestone features such as statues. You can see in the picture here, this building has been made out of limestone bricks, and you can see where the limestone has eroded away by the effects of acid rain. And it has effect on statues as well. This is a statue in Germany, and you can see the effect of acid rain on this statue, the fact that you can't even see the facial features of the statue after the effects of acid rain. So acid rain has big implications on limestone buildings and on limestone statues. And because acid rain is falling, that lowers the pH of rivers and lakes when they fall into the rivers and lakes. So we see a decrease in the pH of rivers and lakes. So in other words, our rivers and lakes are becoming more acidic, and that leads to the death of aquatic life. So the fish and plants and other organisms that live in the rivers and lakes, they will die because they will be used to conditions and they will only be able to survive in certain water conditions. But when the pH of that lowers, they will no longer be able to live in those conditions. And also we see the defoliation of trees. So actually the leaves of trees are eroded away by acid rain. So we can see that the effects of pollution are significant and they can have major environmental implications, both that of the greenhouse effect and of acid rain. And there's ways that we can overcome these issues and minimise pollution, and that's things like burning less fossil fuels. So being careful about our energy consumption, especially when we're using fossil fuels. And if we're burning less fossil fuels, that will lead to lower atmospheric carbon dioxide levels, and it will reduce the greenhouse effect. In terms of acid rain and the pollution caused by it, we can minimise that by removing sulphur from fuels before combustion. So before we burn fuels, take the sulphur out of them, and that will prevent this reaction from happening. Sulphur reacting with oxygen in the air to produce sulphur dioxide, which then dissolves in our rain, as we looked at in our previous topic, to give us sulphurous acid. And that's what causes acid rain. So if we remove sulphur from the fuels before we burn them, we see this reaction doesn't happen, and therefore the sulphur dioxide won't dissolve into the rain to produce acid rain. How we can also minimise it is use catalytic converters in cars, and that will remove particularly those nitrogen oxides that we talked about. And the same idea with the emissions that come from power stations to remove sulphur dioxide. Again, minimising the amount of sulphur dioxide that dissolves in water to give acid rain. And obviously another way to reduce pollution from fossil fuels is to use alternative energy resources, which we've already talked about as a way of minimising the greenhouse effect. But there are economic implications of this. And you don't need to know very much detail about this, but renewable energy resources can be very expensive. Things like wind turbines and wave and tidal generators. They're expensive to build, and also they're expensive to maintain. So you may be asked in an exam ways to minimise the greenhouse effect, ways to minimise pollution from acid rain. But then you may be asked a follow-up question about what are the economic implications of this, or what are the disadvantages of using renewable energy resources. And you want to be talking about the economic implications, the fact that they are expensive to build and expensive to maintain.